Okay guys, so what I want to do in this video is give us a little bit of an introduction into temperature and heat. So now that we've covered just about every type of motion and even combinations of motion, we've looked at motion from the perspective of energy, momentum. We have a huge toolkit that we can use to describe just about any type of motion. Now what we want to do is we want to talk about energy again, but in terms of energy that is not directly related to motion, like not kinetic energy, not our potential energy, but now actually energy in the form of temperature and heat. So in the first part here, I just want to build up our vocabulary a little bit of how we're going to talk about heat and temperature, and then we're going to find like a few ways that temperature affects objects that I want you guys to focus on. So starting out here, are the units. So remember, our units are super important because they let us describe whatever we're going to be looking at, right? So normally we look at temperature in terms of Fahrenheit, right? But in a lot of our problems, what you're going to see is our standard unit is going to be Celsius, right? So degrees Celsius. And you'll even see in some other kind of subject areas, our standard unit can be Kelvin, right? So you can find these on the notes, right? But what I want to do is just show you guys really quickly how simple it is to convert, let's say, from Fahrenheit to Celsius or Celsius to Fahrenheit. Here's our formula that we can plug in whatever our temperature is in Fahrenheit in here, subtract 32, multiply by 5/9, and we'll get whatever that temperature should be in Celsius, right? And here, all I've done is I've rearranged this formula so that Fahrenheit is by itself. So this is the thing we're solving for now. So what we can do is we plug in our value of how many degrees Celsius we have, our temperature in Celsius, and get back our value in degrees Fahrenheit. So what I want you guys to do to try out, this is the important skill for us, is see if you can start with this formula and rearrange everything to get this formula. It should be easy for you guys at this point. I've seen the algebra that you're doing. Everybody's doing really, really well. So what I want you to do is practice this out with these two formulas right here. And that's about as complex as we're going to get with conversions for our exam. So moving on to some foundational concepts of temperature and heat. So a few things happen to objects when you heat them up, right? They don't just contain some more energy and don't change, besides that. They change their form, they change, the atoms and what they're doing is a little bit different. The way they interact with each other is different. So let's take a few of these concepts here. So I've got 3 different concepts that I want you guys to focus on when we're starting out to talk about temperature and heat. The first is thermal expansion. So basically, any material has some rate of thermal expansion. That means when you heat it up or you cool it down, it'll sort of change its shape a little bit, right? And what I have here is linear thermal expansion, okay, or delta L. Remember, this delta just means change. How much does it change over some different characteristics? In this case, it's going to be the change over temperature, right? So let's say I have some metal rod, okay, and then I increase the size of this rod, and I increase the temperature of the rod, and then what's going to happen is it should get longer. Right? This is linear thermal expansion. This actually does happen, right? And you might have noticed this if you ever have something that when it's cold, especially maybe some metal object, gets stuck or doesn't fit as well, or maybe the reverse, like when something is hot, it acts different than when it's cold. Probably that has to do directly with how it is changing structurally with temperature, right? So in this case, very simple, we have some original length at some temperature, and if we heat it up, it will change by some length, delta L, right? So in order to describe this, we have this formula right here, okay? And to kind of illuminate what these pieces are, this here is obviously my change in temperature. okay? And this here is my original length. All of this kind of fitting in with the way we've been subscripting our variables and notation that we've done so far. Okay? The last thing here is this little alpha. And this here is my coefficient. Okay? Oops, so this is my coefficient of linear thermal expansion, right? So let's go ahead and put here. I'm going to put linear expansion. Okay, so this coefficient right here is different for every material. You'll usually be given this, or this will be the thing that you're solving for. Kind of similar to when we were talking about coefficients of friction. Here, our coefficient is just telling us how much exactly does it change with temperature, right? So this is our factor that would separate two materials, maybe one being wood and one being metal, and they change different amounts when you increase them by the same temperature or decrease them by the same temperature. So this coefficient kind of controls this. And just so you guys know, we're not going to focus on it too much, but this same exact idea extends to not only linear expansion, but volume expansion, right? So how does something grow in volume or shrink in volume with temperature, okay? This is the same thing sort of, but in 3 dimensions, okay? And it has a different coefficient, but otherwise you'll see that the structure of the formula is exactly the same, okay? So moving on, we have specific heat capacity, right? So I want you guys to kind of go through the examples that we have and make sure that you feel comfortable with some of these new variables that we're adding in here. Specifically for us, everything here is kind of the same, right? In terms of, this is the mass of whatever we're trying to heat up, okay? And this, of course, is my change in temperature, right? So those are okay, but the two new things here that we want to start talking about, the first one is Q, which is heat energy. And this is measured in joules. Remember, we're still using energy in joules, so we still want to measure this in joules, okay? And the last thing here that we haven't really looked at is this little C. And this is actually our specific heat capacity. So this right here, specific heat capacity, the main focus of this formula is actually this. So what this formula is actually trying to tell us is that if we have, I forgot to write this out for us, if we have a certain amount of a material, right, any material, and we want to change its temperature by a certain amount, this will tell us how much heat we need. Let's say I have 10 kilograms of some material and I want to change its temperature by 10 degrees, 10 Celsius, right? Or 10 Kelvin. Then if I know the specific heat capacity of that material, then it'll tell me how much heat I need in order to make this change, right? So I was going to write here what our specific heat was for water, but we can cover this in the future, right? So I think we'll cover this a little bit more in our homework. So this is fine. This might tell us that we can have, oh, you know what? We can have 2 materials, okay? So here I'll put heat and I'll put temperature on the left-hand side. So maybe material 1 will be something something like wood, right? Like let's say wood, if you pump some heat into it, it'll start to warm up, right? But maybe not as easily as another material, okay? So let's say maybe this would be something like aluminum. Maybe aluminum will heat up a lot more with a lot less heat overall because it accepts the heat more easily. So this C right here is just this measure of how much does the temperature change with a certain amount of heat input. But it's not only this, okay? The last thing that we want to talk about, we want to go over here, is latent heat. Okay, so latent heat, now that we've kind of looked at these things, we know that my Q here, we know that this is heat, and we know that this is mass. Okay, so this is fine. The last thing here is this L, which is my latent heat. Okay? So be careful. You'll notice we have things here like L for expansion, for length, but we also have L here for heat. So one important thing is going to be, first of all, the units of whatever you're looking at. If you have a unit of meters, that is not latent heat. We're talking about length, right? So you want to be sure that you look at the units and not only try to match things by a variable, okay? So I have here latent heat just as a concept is the amount of energy it takes to transfer from one state of an object into another state, another phase, right? So here on the side, I've kind of drawn out, we have water below zero. We kind of know this intuitively, or we have this as common knowledge, that below zero, it's ice. In between 0 and 100 Celsius, it's water. Above 100 Celsius, it turns into vapor. It evaporates, right? Okay, but what's actually going on here? Would we think that this would just go up like this, as we poured in heat? Would it just keep getting warmer and warmer and warmer and then just keep warming up linearly? This actually doesn't happen, right? So the whole thing of why you put ice in your drink is not really to start at a lower temperature, right? The only difference between that would be, let's say, this would be if I start with my glass and has ice in it maybe, and then maybe this would be without ice. We start with just water in there. But this isn't really the case, right? So if we kind of look at what actually happens here. So you'll start with some temperature. Maybe I start with ice, okay? And then we add some heat and it'll start to heat up. But once it reaches 0, something starts to happen. The ice starts to melt. But what the liquid is, in order to transition, okay, from ice into water, we need to pour in some latent heat, okay? And while we're doing that, we're going to be stuck at this little border between ice and water, right? So what you'll have to do here at this point is we're going to have to start pouring in heat, pouring in more and more and more heat, okay, until you finally at some point melt all of the ice. So what happens is if you have a cup filled with ice and water and it's been sitting for a long time, as long as there's still ice in there and everything's kind of at equilibrium, it should be 0 degrees Celsius, right? It will stay 0 degrees Celsius until all of the ice melts, and only then will it start to warm up, okay? So at this point, once all of the ice melts, we'll start to warm up again, okay? Until we get to this next little boundary point. When we get to 100, you're trying to boil water. So what will happen is you want to boil water, and then once the water reaches 100 degrees C, yes, we need to pour in some energy again, maybe a lot more energy this time. All this time we're pouring in more and more and more and more heat, but it stays at 100. So if you have boiling water, your temperature is equalized at about 100, right? So you might think like, no, I've boiled water and it's hotter than that, right? Well, actually, the gas bubbles in the water might be a little bit hotter than the water itself, but the water cannot be above 100 C when we're talking, some standard atmospheric pressure, right? So the water inside your boiling water is never going to be over 100 C. Maybe you have a lot of bubbles in there, so you have like a rolling boil, so all the gas can be over 100, but the water itself is still 100 until it all turns to vapor, right? So at this point, once we evaporate everything, okay, then we can continue to increase even further our temperature, right? So now that we have water vapor, we can continue to increase our temperature. So this latent heat is just a measure of how much energy do I need to pour in at these flat sections in order to change from water to vapor. And it depends on two things. It depends on how much, right? How much ice do I want to melt, or how much water do I want to boil? And it depends on a factor here called latent heat, and this is a constant. So here I have two constants, the latent heat from ice to water. It's always a transition, right? Is 33.5 10 to the 4, and the latent heat from water to vapor is a different value, right? Slightly larger value. So you need more energy to boil water than you do to melt ice. All right, guys, so now that we've gone through this, I want you guys to try out a few examples with each of these questions. Make sure you're comfortable with this so we can start to talk about heat transfer next.